Hello, everybody. Welcome back. Today's topic is Unit 3.12, which is all about the photoelectric effect and the calculations associated with it. So let's get started. So in our last lesson, we talked a little bit about the concept of spectroscopy and what happens when you expose atoms and molecules to certain types of radiation. How do the atoms and molecules respond? And what we're going to focus in on today's topic is what happens when you expose atoms and molecules to ultraviolet or visible light. And I imagine that much of this may be review from Chem 1, but let's go over it anyway. So when an atom is exposed to ultraviolet or visible light, that energy is absorbed, which causes electrons to, quote unquote, jump energy levels. If you will recall from Chem 1, when electrons are in their, quote, normal, energy levels, sublevels, when you think about how you would write out the electron configuration, when they're in their, quote, normal positions, that's ground state. When electrons and atoms absorb energy and those electrons jump to energy levels further away from the nucleus, that is called the excited state, a higher energy state for that atom. And this process has a name. It's called the photoelectric effect. All right. When light waves hit a surface, usually we're talking about metals. Okay, remember what we just said. That energy is absorbed, electrons jump to excited state, but that is a very unstable condition. And electrons will fall from excited state back down to their normal ground state. And when electrons fall, energy is emitted in the form of visible light. If you will recall, one of the things that we said about things on the electromagnetic spectrum, visible light being one of them, is that these are all things that travel in waves. And they are. Photons are ejected off of the surface of these, usually a metal. Those photons would be traveling in the pathway of a wave. Okay, so the photoelectric effect is just an atom absorbing energy. Electrons go from ground to excited, but then they fall back down, and a photon or photons are emitted. Okay. And I said this in our last lesson, everything on the electromagnetic spectrum, these are all things that travel in waves, and so they have some similar characteristics. All right. First of all waves have a wavelength. Okay, the distance between two peaks or two troughs, two valleys in a wave. Frequency implies the number of waves that pass a certain point per second. And another characteristic that they all have in common is that everything on the electromagnetic spectrum, gamma rays, X-rays, microwaves, radio waves, everything, all of those waves travel at the same speed, the speed of light. You do not have to memorize that number. It is on your equation sheet for you. It's a constant. This is an equation that is also on your equation sheet, okay? And it relates wavelength and frequency, okay? So you may be asked to do calculations that involve using this equation. C is the speed of light. Again, that's a constant and it is given to you on your equation sheet. Lambda is the symbol that represents wavelength. And ladies and gentlemen, that must be in units of meters. On occasion, you'll be given a problem where the wavelength is given to you in units of nanometers, and you need to make sure to convert it to meters before you plug it into that equation. That symbol, it looks like a V. It's actually the Greek symbol for nu. That represents frequency, which is going to be in units of inverse second, or a unit that is the same thing as an inverse second. You will sometimes see it in frequencies in units of hertz. 1 hertz is the same thing as 1 inverse second. Okay, so sometimes you'll use that equation. There's another equation that you may be asked to use, which is primarily this one, okay? This one over here is actually combining the equation on the last slide and this one together, okay? But this first one that I've circled, that is on your equation sheet. And it relates the energy of that wave. Energy is going to be measured in joules. H is another constant. It's called Planck's constant. It is given to you on your equation sheet. No need to memorize. And again, nu is frequency in units of inverse second or hertz. And again, if you were combining this all together, your wavelength needs to be in units of meters. So let's look at a sample problem. All right, I'll read it out to you, and then you can pause your video and see if you can solve it on your own. It says the complete photoelectron spectrum of an element in its ground state is represented above. So this is review. We've learned about PES graphs back in Unit 1. Calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell, that's important, valence shell of an atom of this element. So if you want to pause and try it, see how you do. All right, let's see how you did. The first thing I did, guys, and I'm going to put the answer up in just a second, whenever I see a PES graph, whether it asks me to do this or not, I am just in the habit of labeling the graph, like labeling each peak with what sublevel is it. And so let me bring up my answers here. You'll notice that the first thing I did, just look at the graph for now, is I labeled my peaks, okay? I know that this is the PES graph for calcium. Not that that really matters, but that's just something I'm in the habit of doing. Now, the problem said to calculate something for when an electron is removed from the valence shell. And so actually labeling the peaks kind of came in handy here, because I know valence shell means the outermost energy level. So I'm looking right there, which is how I knew which energy value to use. Okay, and then I started my calculations, and I started with the energy equation, solved for the frequency first, and I didn't round it too much because that wasn't my final answer. Then I put the frequency in right there and was able to solve for the wavelength, and since I was solving for the wavelength, my answer came out automatically in meters, which is what they asked for. So this is an example of a kind of question you could see. Let's do another one. All right, it says, in the upper atmosphere, ozone, that's O3, molecules decompose as they absorb ultraviolet radiation as shown by the equation below. Ozone serves to block harmful ultraviolet radiation that comes from the sun. Wonderful. A molecule of ozone absorbs a photon with a frequency of blah, blah, blah. How much energy in joules does this ozone molecule absorb per photon? Okay, there's another question below it, but let's just focus on this one first. Let me just say something before you pause the video. Anytime you see, like you're going to be doing a wave calculation, if you ever see per photon, the equations on your equation sheet that we will use, the ones we just used in the previous problem, are per photon automatically. Let me say that again. The calculations that the equations you'd be using for waves are per photon. So the energy, that we used on the previous slide is per photon automatically. So pause your video and see if you can solve just this first part. We're given a frequency, solve for the energy in joules. All right, let's see how you did. This first part was pretty simple. You're given a frequency and you're asked to solve for the energy, and that's all you had to do. And I typically round my answers to 3 significant figures, and my answer is already in joules. Now, let's talk out the second part of this question together, because this is a little tricky. It says the minimum energy needed to break an oxygen-oxygen bond in ozone is 387 kilojoules per mole. Does a photon with a frequency of blah, 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 the one we just did a calculation for, does that photon have enough energy to break this bond? Support your answer with a calculation. Okay, well, I know how much energy that photon has because we just calculated it. Here's the tricky part, guys. They're asking us if that is enough energy to break apart one oxygen-oxygen bond. This number that we're given here is not the energy associated with just one bond. It is the energy associated to break a mole of those bonds. And that's not what they're asking me. They're asking me, is our photon enough to break just one of those oxygen to oxygen bonds? So watch what I'm going to do here. We have 387 kilojoules for every 1 mole of bonds. Okay. Well, my energy of my photon is in joules, so the first thing I'm going to do is get that 387. I'm going to get that out of kilojoules, and I'm going to get it into joules. Okay, cool. However, if I stop here, that's still not going to help me, because then that's going to be joules per mole, and that's not what I want. I don't want to know is it enough to break a mole of bonds. I want to know, is it enough to break just one? So, how many bonds are in a mole of bonds? This many. Okay, and now we can do that calculation. So let me put that into my calculator. And let's see what we get. All right, I'm going to round to 3 significant figures. I get this. Times 10 to the negative 19th joules. Okay, so we have enough information to answer the question. This is how much energy is required to break one oxygen to oxygen bond. Is the energy that we have a box around, is that enough? Yes, it is. It's more than enough. So we would say, yes, this photon has enough energy to break one of those oxygen to oxygen bonds. Okay. So that problem involved a wave calculation, but it also involved a little trickery with that whole per mole business. Okay, because remember, we were only asked about just one bond. So those are the types of questions you might see about this topic. So I hope you have learned a little something today, and I look forward to seeing you next time.